So this is temperature notes number 2. Write down any vocabulary or ideas or terms you feel is important into your notes because you do have a notes check at the end of this presentation. First of all, some summary of what we know already. Now this is nothing new. You already have this stuff in your notes. 1. Temperature is a measure of friction between moving particles. It also takes energy to get things to move in order to cause that friction. And if you add energy, things move more, which creates more friction. Temperature goes up. We also know that energy to cause this movement comes from the sun. Another piece of summary, once again, this is nothing new here, is that the higher the elevation, the lower the temperature, because there is actually less air bouncing around up here, hitting each other, so you're going to have less friction.
So here I am on the upslope of the Mauna Kea volcano in Hawaii, and I'm at an elevation of about 9,000 feet, so there's not a whole lot of air up here moving around. And you can note from my thermometer the air temperature is about 64 degrees. Well, I'm going to get in the car and I'm going to drive right back down to sea level where there's a lot more air rubbing up against me, and I'm going to note what the difference is in this thermometer on my way down and once I'm down at the bottom. Now let's take a look at the difference in the temperatures from up there at 9,000 feet to down here now at sea level. Because there's so much more air down here than there was up there, there's a lot more friction because there's a lot more air rubbing back and forth against each other. And you can see how high the temperature has gone up, almost 20 degrees, and I've only driven about 30 minutes away from where I was. The difference is there's more air here at sea level, so there's more stuff rubbing together, hence more friction and higher temperature than at the higher elevations where there is less air moving around, making less friction.
We now also know that water does not change temperature easily, so places near the water don't heat up and cool down as much as places away from the water. We use the example of Hawaii, which is an island in the middle of the Pacific Ocean. So much water around it, it's just not going to get too hot and too cold. San Francisco, California is on a peninsula. It has water on all sides of it. It's surrounded by so much water that doesn't heat up and cool down that San Francisco pretty much has the same temperature all year round. Florida, because it is a peninsula that sticks out into the water, so it is surrounded by water that doesn't change temperatures too much. Therefore, the state of Florida does not change temperatures significantly.
So here it is, April 29th. It's a nice, bright, sunny spring day. It's April 29th, so we're well past the equinox. The sun's really high in the sky, and we're getting a lot of direct sunlight. And it's the time of the year our temperatures really start to heat up. But if you'll notice the sky, there is not a single cloud up there, which means we haven't gotten into that hot, humid days of summer yet, and it's still a chance that we get really dry air, and you can see that in the sky. The humidity today is 24%, which is just insanely low for Georgia. What this means for our temperatures, if you can see this, this says about 77 degrees standing out here into the direct sunlight. And that makes sense. It's no water in the sky, very dry air, a lot of sunlight, so dry air will heat up very, very quickly. But we're going to come right over here and we're going to stand in the shade and watch what happens to the temperature once I press the hold button. Look how quickly the temperature starts to drop. There was a big change in the temperature from out there in the sunlight to over here in the shade, and that's because the air is exceptionally dry, and dry things change temperature easily, wet things do not. So over there in the sun, it's 77 degrees. Over here in the shade, it's dropping. It's going to be less than 65 degrees. A 12-degree temperature change in a distance of about 20 feet. And that's just because we have such dry air that heats up and cools down very easily. If we do the same experiment in the summertime, we wouldn't notice the big change in temperature because the air would be humid, and wet things don't change temperature very easily.
Okay, so we understand the importance of water and that how if you're near the Pacific or the Atlantic Ocean, your temperatures aren't going to change a whole lot. But as it turns out, there's a difference between the Pacific and the Atlantic Ocean in terms of the effect they have on temperatures. And it has to do with how wind moves in our country. Primarily air or wind in our country moves that direction. So if I am over here on the West Coast, the air that is coming to me is always coming to me from over the Pacific Ocean. The Pacific Ocean pretty much always has the same temperature because it's such a big body of water, it doesn't change temperature that much. So I always have about the same temperature. But if we go over here on the East Coast, the air that is coming to me has gone across the United States. Well, that's a bunch of land, and that land can have significantly different temperatures. In the summertime, because it's a bunch of land, that air gets to be pretty hot. And what comes to me is hot air, so I'm hotter. But in the wintertime, this part of the country can get cold. So what comes to me is cold air. So on the Atlantic coast, my temperatures change a lot more than on the Pacific coast because the air that is coming to me is coming from over land, and that land can be either hot or cold depending on the season. But let's clarify something. A location here on the Atlantic coast, a location here that is not on the coast. The location on the coast is going to change temperatures less than a location that is not on the coast. However, the East Coast changes temperatures a lot more than the West Coast. So there's a big idea, big conclusion. The temperatures in the U.S. change much more on the East Coast than the West Coast because of how the wind blows across our country. That's going to be something we have to look at when we're trying to say, well, how much is the temperature changing here? Or how hot or how cold is it? Yeah, it's on the water, but the Atlantic coast and Pacific coast have different influences over an area's temperature. Now, there is another big factor that we got to get to. And I want to ask you this, where is it cold and where is it hot in the United States? Well, you guys know this. You know that generally we say it is cold up north, and we would generally say that it is hot down south, and you would not be wrong in saying that. Here's a little graphic of the hottest and coldest cities in the United States, and you'll see what we already know to be true. It seems like all the cold cities are up north, and it seems like all the warm cities are down south. And that is true. The question becomes why? Why is it cold up north and hot down south? Take a look at these average annual temperatures. Texas is 65, Oklahoma is 60. Look at this pattern. As you go north, notice what happens to the average annual temperatures. It gets colder up north. It's warmer as you go south, and it is colder as you go north. Once again, the question becomes why? Well, let's review again. Temperatures are a measure of friction, right? Which is from moving particles, air. And air moves because it's got the energy to move, and all that energy comes from the sun. But if we're all sitting under the same sun, shouldn't everything have the same temperature? Well, here's breaking news, and that is that the sun is not the same up north as it is down south. Now, physically, the sun is the same, but the energy we get from the sun is not the same up north as it is down south. It has to do with how the earth is curved. Because the earth is curved, sunlight that hits the earth here in the middle hits at 90 degrees. And as you go away from the equator, you'll notice the sun gets a little bit more spread out because the sunlight is not hitting the planet straight on. It's hitting it at some angle that is less than 90 degrees, and that greatly impacts the temperatures. And we're going to look at why.
So let's take a look at how the angle at which the sun's rays hit the earth will affect temperature. I'm going to use this light here, and I'm going to focus my sunlight at 90 degrees from this lamp. The lamp is straight up and down and it's vertical, and you'll notice all the sun is concentrated in an area that big. But if I change the angle at which the light hits the table,
now I see that the sun's rays are spread out over a much wider area. That means a person here is getting a lot more sunlight than someone here when the sun's at an angle, because the sun is a lot more spread out. Well, the less concentrated sunlight you get, the less energy you get. The less energy you get, the slower your particles are going to move, and therefore you'll have less friction and hence a lower temperature. So the angle at which the sun rays hit your location greatly impacts your temperature. The bigger the angle, the more spread out sunlight is, and the lower your temperatures are going to be. So the sunlight that hits the Earth at a high latitude, away from the equator, gets spread out over a much bigger area. That means any particular person or location in that spot is actually getting less sunlight than someone who's standing at the equator, who's getting the sunlight directly over the head. Well, the less concentrated your sunlight is, the less energy you're getting from those rays, and hence you're going to have a lower temperature. You can kind of see it here. Here we got my little Bart Simpson character. You can kind of see he's getting all of the sunlight in that little area right there. It's all very concentrated. But here, when the flashlight was held at an angle, like the sun hitting the Earth at an angle, the energy from the flashlight, or the energy from the sun, is spread out over a much larger area. If you're getting less sunlight per area, you're getting less energy. You're going to have lower temperatures because you have less energy to move, which is going to be less friction and hence lower temperatures. Now here I'm going to test the sun angle for you. Took two locations on the same day, June 21st. Different years, obviously, but I compared Hawaii and Atlanta. And I went outside and I took a 12-inch ruler and I held it vertically outside, and I looked to see what shadow the sun made with that ruler, because the higher the sun is in the sky, the smaller the shadow is going to be. And you'll notice over here in Hawaii, at solar noon, or that point of the day where the sun is highest in the sky, in June, there was almost no shadow caused by that ruler in Hawaii. That's because the sun was so much directly overhead. It was coming down on top of you almost at 90 degrees. The sun was very concentrated. But in Atlanta, we had a much longer shadow, which means the sun was at a lower angle in the sky, meaning the sunlight was a little bit more spread out and not as intense. That has a name. That's called insolation. Insolation is the spreading out of sunlight due to the curved surface of the Earth. So the higher you are in latitude, the further away you are from the equator, the greater the insolation. The greater your sunlight is spread out, and hence the less energy you get and the lower your temperatures are. You can see that here's a thermal energy image of the Earth, and you'll notice that the highest energy and highest temperature sections of the Earth are right there in the middle, because that's where the sun tends to be more directly overhead and sunlight is much more concentrated. As you go away from the equator, either direction, and the Earth is more curved, the sunlight hits you at an angle and is therefore more spread out. You get less sunlight and hence lower temperatures. So, another big conclusion: the farther away from the equator, or the higher the latitude, the lower your temperatures, because sunlight is more spread out. So we've been alluding to the fact that temperatures change between summer and winter, and those are our seasons. And we know that there is a difference in temperature from fall to winter to spring and to summer. But now let's look at the reason why we have seasons, and why do temperatures change from one season to another? Well, why do temperatures change throughout the year? Why do we have seasons? If we think about what we know about temperatures, we have distinctly different temperatures, but aren't we always under the same sun? And if all the energy comes from the sun is not changing, why do we have seasons? If you ask most people out in the street, 99 times out of 100 people are going to say, well, it's in the wintertime, we're closer to, we're further away from the sun. In the summer, we're closer. So, the energy gets stronger. And you would be partially correct with that assumption. But here's the kicker. Yes, the Earth is actually closer to the sun, but it's in January, not in July. The sun is actually 4 million kilometers closer to the Earth in January than it is in July. That seems kind of backwards. Oh, why shouldn't we be hotter? Well, because 4 million kilometers really doesn't make much of a difference in terms of the amount of solar energy that you receive. So, this is a very common misconception that the seasons are caused by the Earth being closer to or farther away from the sun. That's not it. First of all, the word season. The word season is derived from a Latin word that means to sow, as in to put your crops in the ground, to sow your seeds into the ground. So the seasons were based on when it was warm enough, or more closely to say that when there was enough sunlight for plants to grow. But why does sunlight change throughout the year? If it's the same sun year round, how can the sunlight change? Well, it has to do with this. And this is the fact that the Earth is tilted at 23.5 degrees on its orbit as it goes around the sun. You might have noticed we played with these globes before, and you've seen globes, and you'll notice that they're never straight up and down. They always have this tilt, and that's how they spin around that axis there, because that's a very accurate portrayal of how the Earth is physically oriented to the sun. It is tilted at 23.5 degrees as it's spinning and rotating around the sun. Well, what that means is that half of the Earth doesn't get the same sunlight that the other half gets. Here's my light that mimics the sun, and you can see how it's illuminating part of the globe, but it's not illuminating both parts equally. You can see here, this will be representative of December 21st, and you'll notice that the bottom half of the Earth, the southern hemisphere, is getting a lot more sunlight than this part up here. You can actually see the part of the globe that is lit up by that light bulb. Well, if you're getting less sunlight, that means you're getting less energy and your temperatures are going to be lower. This is what happens to give us winter. It's when we are tilted, in this case, our hemisphere, here's the Earth's tilt, and we're tilted kind of away from the sun, so we're getting less sunlight. On December 21st, you might have seen a picture like this before. It shows you the part of the Earth that is illuminated by the sun. You'll notice down here, there's a pretty good sized area of the Earth that's getting lit up by the sun. But yet, at an equal latitude north of the equator, the area or part of the Earth that's being lit up by the sun is much smaller. So that you're actually getting less sunlight in the northern hemisphere on December 21st than you are other times of the year. Look how much more darkness you have. And the more darkness you have, which means you're getting less sunlight in the day, which means you're getting less energy, and you're going to have colder temperatures. So we have something like this. Here's a picture of my sun and my Earth that is tilted as it moves around the sun. And you'll notice that this picture is oriented the same as my globe here. There's my axis of rotation. Here's my northern hemisphere. So in this picture here, the northern hemisphere is kind of tilting away from the sun. So as the sunlight's hitting it, it actually has a smaller area that is lit up, getting less sunlight, meaning you have lower temperatures. That's what winter is for us. Now, the Earth doesn't stay in one place. 6 months later, the Earth is over here. And now we've got the opposite effect, where more of our hemisphere, the northern hemisphere, is lit up. You can actually see it here. This would be an example of June 21st. Now, the axis of rotation is like this, and our hemisphere up here, the northern hemisphere, is kind of leaning into the sun, and the southern hemisphere is kind of leaning away. That means up here, we're getting more sunlight. Down here, they are getting less, and you can see by this outlined area, there's actually less of the southern hemisphere lit up than the northern hemisphere. So here we got June 21st. June 21st, that's the length of the sun, or length of the daylight in the southern hemisphere. Look at it up here in the northern hemisphere. It's a lot bigger. The southern hemisphere has a lot more night than they do day, meaning they're getting a lot less solar energy. It means you're going to have lower temperatures. Up here, notice the daytime is much larger than the night. So you're getting more sunlight because the days are longer, hence you're going to have higher temperatures, which we know to be true in the summertime. So we get this. We get that over here we're going to be tilted away from the sun. Here we're tilted towards the sun. So this is going to be my summertime over here where I'm leaning into the sun. This is going to be my winter time. But what about in between? We know we just don't skip from summer to winter. We go through the other seasons. Well, what's happening with sunlight then? When the Earth is right here in the middle, here's the sun, like my light bulb, and the light is hitting the Earth like this or like this. Well, in this case, one hemisphere is not tilted more towards the sun than the other. Both hemispheres are getting the same amount of sunlight. And that's the point. That's the day that marks a change from one season to another. In this position, where the northern hemisphere is getting the most sun because they're tilted towards the sun, that's our summer. Over here, that's our winter. Well, if I tell you I'm in summer and I'm going this direction, what comes next is fall. Fall is that day where we're kind of in the middle, in between the start of summer and winter. Same thing going the other way. Go this direction. We know that this is going to be spring, the halfway point between the start of winter and the start of summer. So let's look at March. March 20th is that day. It's that day where we switch from winter to spring. Notice the length of the sunlight in the northern and the southern hemisphere is the same. The length of the nighttime for the northern and the southern hemisphere is the same, and they're about equal. You got about the same amount of sunlight as you have, same amount of daytime as you have nighttime. And that is true about that date in March. That's what's special about that day in March. That date, there's the day where we transition from one season to another, where our amount of sunlight goes from being more in the day to more at night, or vice versa. Now, same thing is true when we come this way, except it's happening in opposite. Instead of we're going from winter to summer, now we're going from summer to winter. And there's still that day where the hemispheres have equal sunlight, and you're going to transition from summer to winter as opposed from winter to summer. Same thing. You'll notice in September 22nd or 23rd, roughly, the sunlight's equal in both hemispheres. And the nighttime is equal to the daytime. So you don't have more day or night, you have about the same. And that's a special day that transitions from one season to the next. Now, because the Earth is tilted as we go around it, we don't always see the sun in the same place in the sky throughout the year, because we know that we're going to see it higher in the summertime and lower in the winter. It looks something like this, because in summer we're tilted more towards the sun. The sun is higher up in the sky, as opposed to wintertime when we're looking away. We're tilted away. The angle of the sun in the sky is much different, and we see it much lower in the sky. Something like this. In the summer, June 22nd, the sun might be way up here. Make that angle. In March and September, those special days where the sunlight is equal in both hemispheres will kind of split in the middle. But in December, that sun's going to be way lower in the sky because our hemisphere is pointing away.
So today is June 21st, or the summer solstice, the day where the northern hemisphere is tilted most towards the sun, and that means the sun is at its highest point in the sky. Now, I'm outside today at what's called solar noon, or that time of the day where the sun is at its highest point in the sky. Well, I have this device right here, and the sun is hitting this ruler and it is casting a shadow. The length of the shadow depends upon how high the sun is in the sky. The higher the sun is in the sky, the shorter this shadow is going to be. So we're going to measure this shadow today in the summer solstice and see what the length of that shadow is, and that can tell us how high the sun is in the sky.
So here's my results on June 20th versus September 24th of the angle that the sun is in the sky in Atlanta. Now, I haven't changed latitude here. I'm in the same place, right out in front of my front yard, in front of my house. But you'll notice that in June, the shadow is only that long. But in September, the shadow is this long. Well, that means the sun must be lower in the sky to make the shadow longer. So this proves to us that the sun's position in the sky is changing throughout the year. Well, the sun's not moving. It's in the middle of our solar system. What's different is the tilt of our Earth as we go around the sun changes the angle at which we see the sun. And I can see that makes my sunlight a lot more spread out in the winter than it is in the summer. Well, if the sunlight is spread out, that means the sunlight energy is spread out. And if you spread out the sun's energy over a larger area, notice the difference. Now, we don't need to get the numbers, but here we've got a value of 342 watts per meter. We've got 342 watts of solar energy in a square meter. But when the angle is 45 degrees, that lowers to 242 watts per meter. So you're getting less energy per meter of space, which means you're definitely going to have lower temperatures because you're getting less energy. Now, what would happen if the Earth wasn't tilted on its axis? If it was just spinning around, if it was straight up and down? Well, we wouldn't have seasons. And everybody would have the same temperatures year-round because your sunlight would not change throughout the year. Now, I'm going to give you a note sheet to take some notes on about this diagram. You won't have to draw the diagram, but you have to understand what's being said on it. I'm not going to narrate over this so much as I am just going to have you pause and summarize what you see. And if there is something that you write down that you are not sure of, you don't understand, it is your responsibility to ask, hey, what does this mean? Now, this I do want to describe a little bit. How can we tell fall and spring equinox apart? Because they look the same. They're both getting the same amount of sunlight. It's easy to tell the solstices apart because you're tilted most towards or most away from the sun.